Good morning. I'm Trent Parado, Public Affairs Officer at NASA headquarters in Washington. I'd like to welcome you all to the International Space Station Science NASA Social. I'm joined here at the headquarters auditorium by about 150 guests for a very special NASA Social to hear about some of the groundbreaking research taking place daily on the International Space Station, some 240 miles above the Earth. For those joining at home who might not know, a NASA Social is an event where we ask people following one of NASA's social media accounts to come to a NASA center for a behind-the-scenes look at some of the work we're doing. We hope you're all inspired by the human spaceflight endeavors you hear about today, and that you share that experience on social media, and the people following you are inspired to learn a little bit more about NASA's mission as well. Everyone can join the conversation today on Twitter, Facebook, and Google+. Our hashtag today is NASA Social. Today's a very special day in NASA history for those who don't know. 51 years ago, John Glenn launched aboard Friendship 7 Mercury capsule and became the first American astronaut to orbit the Earth. A big part of the legacy of that half-century of American human spaceflight is that we're now able to conduct scientific research in space impossible on the Earth aboard a fully operational International Space Station. The discoveries enabled by the orbiting laboratory benefit humanity and vastly increase our understanding of how humans can safely work, live, and thrive in space. You hear a lot more about this from a great and very exciting lineup of speakers today. I want to jump right into it, and that includes a special opportunity to hear from the crew directly. So let's go ahead and get started. Our first guest is Bill Gerstenmaier. He's NASA's Associate Administrator for Human Exploration and Operations. In this capacity, he provides strategic direction for all aspects of NASA's human exploration of space. This includes the continued operation and utilization of the space station, the development of the Space Launch System rocket and Orion spacecraft that'll take us farther into the solar system than ever before, and the commercial crew and cargo programs that provide logistics and will provide crew transportation to the International Space Station. Please help me give a big NASA Social welcome to Bill Gerstenmaier.
Thanks, Trent. It's my pleasure to be here today and talk to you folks. What's the general plan here, Trent?
Just going to ask for your slides.
Okay. So if we can just go ahead and pull up a couple of my slides, we'll kind of go through some things. We'll do it keep kind of informal, but since I'm from NASA, I have to have slides. So without slides, I'm not capable of talking or communicating to folks. So we'll throw a couple slides up and we'll talk to you a little bit about what's going on. If we could do that, hopefully.
The first slide behind you, we'll get it on.
Okay. Yeah, we'll get it. Okay. Okay. I can't see them behind me, but okay, there we go. We don't have it down here, but all right. Next slide. This is who you're going to be talking to. The crew is on board this wonderful facility you see in this picture. This is the International Space Station. It's about the size of a football field. You can look outside. There's a model outside the auditorium here. You can see how big it is in relationship to a football field and see what it is. It's an amazing research facility. And if you look at it, you know, the crew lives in that little center section in the middle, and then all that other stuff on the outside, the solar arrays, the radiators, and all those things, that's the infrastructure that supports this wonderful research facility. So if you think about it, you know, when you live at home and you get power and you turn on water, there's a huge infrastructure that supports all those things in your home. It's kind of the same thing here. Our research facility is supported by those large solar arrays and radiators and things on the outside. You can also see that little arm sticking up in the middle. That was the Canadian arm that actually allowed us to assemble large pieces of this space station in orbit. So as you know, it took a bunch of flights, I think 30 or so shuttle flights, to actually assemble this wonderful facility in space. So what you're seeing here is an unbelievable international research facility. Next. You know, I think of space station as really the first step in exploration, and these are just two pictorials of what's coming next. This is the Orion capsule in the big picture there. You'll notice it now has the rectangular solar arrays. It used to have round solar arrays. When we made a deal recently with the European Space Agency, they're going to help manufacture that service module that sits behind the capsule itself. It provides the power and propulsion for the capsule. And we did that with the Europeans. This is in development. We're going to fly this as a test flight in 2014 down at the Cape, and we have the crew modules actually down at the Cape right now undergoing outfitting, and they're putting it together, putting all the electronics, avionics, wiring, all the stuff is going inside the capsule for that test flight. It'll be uncrewed, but it'll fly in 2014, so that's pretty exciting. And then over on the left of that picture, you can kind of see the big rocket. That's the Heavy Lift Launch Vehicle. It'll be one of the largest rockets we had. It starts out at about 70 metric tons to low Earth orbit, and it grows to about 130 metric tons to low Earth orbit. We need a rocket that big to go to destinations as far as Mars. And if you look at what it takes kind of vehicle-wise, that station picture I showed you, that's 900,000 pounds in orbit. To take a crew to the surface of Mars and back will require about that same mass in orbit, so roughly 900,000 pounds. So you don't want to do that over 30 shuttle flights in 10 years. You want to do that with a bigger rocket that can carry a lot more, and that's what the purpose of the Heavy Lift Launch Vehicle is. But I think of Station as that first step in exploration, and then it's followed by these vehicles. So what we learn on Station will directly apply to the things we're going to do as we go to Mars and asteroids and moons and other locations. Next. On board, next slide, please. On Station, there's some plants that are growing. I look at these as two things. What's exciting about this is it teaches us about how plants really grow. So you remove gravity and what causes the plant to grow up. Is it light that causes it to grow up? Does gravity have an influence? How do the roots grow? You really get some insight that you don't normally get here terrestrially. The other thing is genes express differently in space for some reason, and plant genes also express differently in space. So we're growing these plants in space to understand how we can better produce crops here on the Earth. And then also for exploration, we'd like to take some plants with us on exploration so we have a food source for our crew. So I consider this kind of a dual purpose thing. We're learning about things that can help us here on the Earth and can also be pretty beneficial in space. Next. This is some future technology. This little module will be added to the side of Space Station. It's an expandable technology. So when this package comes up, it's compact and it's all folded up. It's made out of fabric. It's probably about 6 inches of fabric all folded up tightly. And then we inflate it and expand it. And what this does is this gives you tremendous volume for a very small on-orbit volume going to space. So as we think about going large distances on the way to Mars, you want a nice big habitat for the crew to live in. Maybe you don't want to launch that big a habitat, so we're looking at inflatable structures. So we'll do that on board Space Station in 2015. We'll fly this up and attach it to Station, and we'll get a chance to experiment with a new module design. So instead of having all these hard shell aluminum devices, or habitation modules, we'll get a chance to have some expandable technology. So this is another thing that Station's doing. Not only doing research, but it's allowing us to experiment with new hardware, new ways to build things as we go forward in space and in exploration. Next. This is just another picture that I think is really unique. Station teaches us a lot about the Earth, and you can see this image taken of the Earth below, and you can really see where the cities are. It turns out that where we live, especially at night, we generate a lot of lights in those areas, and they really define us as a human species here on the Earth. And I think Don will talk to you some more about some of these images, how he actually took them. Some of the crews will talk to you about it, but I think it's neat to get this perspective of what the Earth looks like. The other thing that always impresses me too is really how thin our atmosphere is when you think about it in this picture. We live in that little tiny space, so when you fly in an airplane, you're down in that little tiny, thin atmosphere that sits around this Earth. So that's a very different construct than the big vastness of space. And you can see the star field, and you can also see some auroras kind of out in the distance. But this is a pretty unique and amazing picture. Next. This is another big thing on Space Station, is it's really an international endeavor. You can see the crew members, they all have patches from their countries on their shoulders. There's a Russian in the middle, an Italian, and then an American, Katie on the left. Or right, and it's pretty neat to think about we're in space with an international crew. Even when you talk to the crew today, you'll be a Canadian there with the American crew members. So again, and the Russians will be off busy doing things on the other side of Station. But again, this international relationship and working together and building this international research facility is a tremendous other benefit of Space Station. So, I think of the Russians really now as truly our partners. We share data back and forth. They fly our crews to space. We really operate in a very seamless manner and share a lot of information. So this is a tremendous benefit of Station. Next. This is some of the commercial cargo capability that's coming up. This is the Dragon capsule. It's being captured by the arm. I think Don may have done this capture in this picture, so you can ask him about that, how it was to take the arm. I think he practiced for several days before. I happened to be in Houston and listened to him on air to ground. So, it's like a skater or an athlete. you see the big event and it looks really great when it occurs. You don't realize all that practice and all that homework that went the many days before. And Don was evidence to that. He'll tell you how much he practiced the day before along with the folks on the ground to make sure that when the big game day came, he was ready to go execute and grab the capsule in exactly the manner, and there would be no problems at all. And it worked out extremely well. This is getting ready to launch again next Friday, so this is pretty exciting to see these new commercial providers come online and bring us a new way to get cargo to space station. Next. This is another provider that's coming online. They're down at Wallops here in Virginia, pretty close to us. They have their rocket out on the launch pad. They're getting ready to do a hot fire test. They'll probably do the hot fire test this Friday or Saturday, and then the next week, as I said earlier, the Dragon capsule launches. So a pretty exciting time in cargo delivery. All these new vehicles are starting to launch to space. What's exciting is they have to fly more often than the shuttle did, so that allows us to get cargo and research back and forth from station a little faster than we did even with the shuttle. So there's some real advantages to these cargo providers. It'll be pretty exciting to see this thing launch from Wallops. I think if you're here in DC, I think if you get up on a rooftop somewhere and you look out to the east the right way, you may actually even be able to see the launch here from the Washington area. So that's something to write down. And maybe we'll see if this all works out, and then you get a chance to actually see a launch here from DC, which would be pretty special instead of going down to Florida. Next. Again, on the other side, this is the future for crew transportation. We're working on commercial crew transportation, buying services. These are the three contenders on I guess the left of your screen is the Boeing capsule. The center one is Sierra Nevada, a winged vehicle, and then the right is the Dragon capsule. So again, we're starting that work now. We're doing the development activities with them. We've issued some small contracts to begin work on this area, but it's pretty exciting to see these new commercial providers come online with a new enthusiasm to deliver our crews to station, and it'll be great to have them online. So then if there's a problem with the Soyuz and we need a backup, we have a U.S. capability. So it'll be really super when that happens and comes online. Next. This is one of my favorite pictures, and I'll give you a little context. This is the shuttle, obviously, which you see. This is the shuttle coming to dock at the space station. I think it was around STS-120. What's special to me is that the human crew, 6 crew members took a picture of 7 crew members in that little shuttle. And then down in the dark region to the left, that's flying over Chile. So there's also the Chilean population was taken in this picture. You can't quite see them there, but they're there. So there's maybe 7 crew members or 6 crew members on board space station taking the picture, 7 on the shuttle, and a couple 100,000 down in Chile at the bottom of the picture. The other thing that's interesting is the orange region. That's the region of the atmosphere where the weather occurs. So when you have rain and thunderstorms and all those things, that's where that occurs. Then that little white region, that's the region above the stratosphere, above where the weather occurs, and then it starts fading into space. And then if you think that that's deep space, that dark thing out on the right-hand side, that's not it. That's the window frame. So we kind of fake that to make it look good. But it's a pretty neat image when you think about this. And I think about this, it makes me sad sometimes. I worked in the shuttle program a long time. The shuttle's not flying anymore. But then if you think back to those other pictures I just showed you, the future is commercial cargo, commercial crew, and then the capsule beyond low Earth orbit, pushing out into the universe, going well beyond low Earth orbit, back out to the moon distances, out to asteroids and Mars. It's a pretty exciting challenge. So we gave up a pretty special vehicle, but we gave that vehicle up with a pretty bright future. So our job in the agency is to make sure that that future occurs, and that's what we're working every day, is we're using the space station as that first step in exploration, and we're moving out and going to do great things in space. And then the last slide just gives you some web links and some things to go pull up some data. So that's all I wanted to talk to you about. So again, enjoy your time here. Thank you for all you do. You guys tweet in a unique way. You bring a unique aspect of our business. We sometimes get a little maybe down because I'm dealing with Congress and politicians and lawyers and other folks. But then to have folks that are enthusiastic, excited, want to know about science, can resonate with the cool stuff that's going on, then I get charged, and then I can go back over to the Hill. I can go talk to those lawyers and those staffers, and I'll give them heck. So I'm going to take your energy today, and when I go talk to Congress, it'll be your energy being delivered.
Okay, so we have a couple of microphones in the audience. Let's do some Q&A, and we'll start here. I'm going to go ahead and queue up a few. That'll be the next one. And then,
Hi, my name's Zayden, and I have 2 questions. One is, why is Orion going to have 4 solar panels?
It's going to have 4 solar panels so it can generate electricity to keep all the computers and all the systems working so they can communicate and talk to the folks on the Earth, and can keep the life support system, keep oxygen generation working, remove carbon dioxide. So it's the power. It's the electricity that comes into your house comes from those 4 solar arrays.
My second question is there a backup way instead of from Soyuz?
Yeah, right now we're totally dependent on the Russians to deliver our crews to and from space station. But those new vehicles I showed you, the Boeing CST-100, the Sierra Nevada Dream Chaser, and then the Dragon capsule, those 3 are coming online. So we have 3 people that are building another way. They'll probably fly in 2017, which is seems like a long way away. That's 4 years away. But for a while, we'll be dependent upon the Russians to deliver our crews back and forth. And when we had the Columbia tragedy, the Russians helped us, and they kept us with a crew on board space station for that entire time by using the Soyuz. So we're not doing something totally different than we've done before, but we want to get another way to bring crew to station as soon as we can.
Thank you.
I think we just met the future NASA administrator.
Yes.
I should have said this at the end. Please stand up when you ask your questions. We'll go here.
Hi, I'm curious about the expandable capsule you were talking about. I was wondering how, if micrometeorites and other space junk are a concern with a soft capsule like that.
Yeah, and what we're really doing with space stations, we're going to get a chance to see how it really operates in space. It's pretty thick if you look at the material, and it's Kevlar. So it's very, very tough and durable. We don't think it'll have any micrometeoroid problems, but we'll actually get a chance to see how well it performs. The other advantage is from a radiation protection standpoint, when radiation particles travel through aluminum, they hit the aluminum and then they tend to splatter into smaller secondary radiation events. Those can be just as problematic to the human as the primary particle going through. With the fiber material on the outside, we don't believe that scattering will occur. So then you could put like a water layer on the inside, and that could absorb all those particles, and they won't be as problematic to the crew. So that's another thing we want to go look at when we fly this on station. And then the last thing is, it's so thick, it has very stable thermal properties, we believe. So we won't see the big thermal fluctuations we do in a typical module, we believe. So again, we're going to fly at the station to make sure all this stuff works. So we'll get a chance to see how well it does with micrometeoroid debris, we'll see how it works with radiation, and we'll see how it works with thermal. And that'll be really important for us if we want to use one of these modules for exploration. So station is an unbelievably great test bed to test those exploration technologies as we move forward.
Hi, Rocketman528 on Twitter, Jeff Wallace. Can you walk us through some of the upcoming important commercial crew milestones that might get us all excited?
Okay. In terms of the milestones, I would say for cargo, again, the launch a week from this Friday out of the Cape with the second Dragon flight. That's pretty exciting. For the first time, we'll have cargo in the back. We call it the trunk of Dragon. There'll be some grapple bars in the back that will actually come out and get attached to the radiators. So the first flights, we didn't use the trunk, but now we're going to use the trunk. And eventually this module that you see on the screen right now in front of you, the inflatable module, it actually rides up, that inflatable module actually rides up in the trunk of the Dragon. So we're actually learning how to carry cargo on the outside as well as the inside with the Dragon capsule, and that's the first time coming up. The hot fire test for the Antares rocket at Wallops, that'll be pretty exciting. That's a brand new launch pad, has not been used for a rocket launch before, so that's a pretty exciting thing coming up. And then in the cargo and the crew world, there'll be there's been some test firing, some parachute things, some abort tests will be coming up. So there's quite a bit going on in the crew world. But I would say for me, more near term is to see how well this cargo stuff comes online, and can we really get a good supply chain back and forth to space station.
Can I see hands for a second? Questions? Okay, we'll take this one and that one, and we'll do one more in the back. Go ahead. Yep, this one first.
Hi, I was wondering if you could compare the size of the launch vehicle for your deep space, the Mars probes and everything, to the Saturn V, how big it was to launch the Apollo programs.
Yeah, the SLS will actually be a little bit bigger than the Saturn V, and I don't remember exactly the dimensions, but it's a little bit bigger. We can actually get you probably a graphic that shows you the three rockets compared, where we were with Shuttle, where we are with where we were with Saturn, and where we are with SLS. But it's a little bit bigger and has a little bit more launch capability than we did with Saturn.
Okay, we'll do one in the back here.
Hi, you mentioned that we would be going to asteroids and Mars with manned crews. What's the advantage of having a manned crew visit Mars versus just a probe?
Well, I ought to ask you guys. What do you think the advantage is of having a crew there, right? Would you rather be out on the street and watch this on video, or would you rather come in here and actually participate and interact, right? I think there's a real advantage of the human being there, because the human can react pretty much in real time. If you look what the rover's doing on Mars, you know, it's pretty exciting. You know, you can see the two holes that got drilled in the rocks that are pretty exciting. But then if you look what the Apollo crews did in just one sortie across the moon with their prospecting and looking and being able to find rocks, the human has this unique ability to analyze a situation that wasn't pre-programmed and find things in a different way. You even see it on our experiments on station. You know, sometimes something doesn't work exactly the way the experimenter planned, and the computer would have a real hard time dealing with that, but having the human presence there can adapt to that. So I think there's a right mix between both. I don't think it's right to do all human exploration, and it's not right to do all robotic exploration. It's that right mix between the two, and we're still trying to exactly find that right mix. But we've got 2 robots on board Space Station, at least, that are doing pretty exciting things. We have Robonaut on the inside. He has hands like you and I do, and we're looking at actually throwing switches, and he holds up a fan to measure the velocity through the air ducts to make sure that all the filters are clean. We've got a robot on the outside called Dexter. It's like a machine robot, like you'd see probably in an auto assembly factory. It's out there. We've done some refueling things where we went to a mock-up of the outside of a spacecraft. We actually removed a cover, pulled a blanket off, removed a fueling cap, and hooked up a refueling coupling to actually demonstrate propellant flow into that. So there's a nice mix between the robot and the human. So you see it in underwater experiments with ROVs and other things. And there's a right mix between those two. But I think that human, although it's tough bringing the human there because you have to bring life support and all the food and all the normal things that support us, but then you get a tremendously flexible, intelligent device, the human, that can actually do some amazing things and deal with things in a different way. But you ought to think about it yourselves and imagine if this task was done with a robot or was done with a human, what do you see as the advantages? And those would be good things to go tweet to your friends.
Maybe one more question here in the back left.
I'm Joe Constant. Are there plans to start using the Western launch sites more, such as Vandenberg?
There will be some launches from Vandenberg for expendable satellites using the SpaceX system. We just had the Landsat data continuity mission was just launched out of Vandenberg. That's an Earth observation satellite that provides a lot of images of the Earth. It has a spectrometer on it so we can look at crops, look at forest fires, those kind of things. It's a continuation of the basic Landsat mission. So there'll be a fair amount of launches out there, but almost all our human missions will come off the East Coast as we look forward. All our station missions will also probably come off the East Coast.
So before we start the downlink, I just want to plug the @ISS Research Twitter account, which you can follow, and it's actually pretty active. At least a couple times a week, we have new content that shows some of the investigations and experiments that are happening on station. Maybe have time for a very, very fast question if we're lucky. Does anyone have a quick one? Let's go right here.
Hi, Gerst. What are the plans in process now for extending the life of the space station beyond 2017, 2020, and what is its usefulness in maybe launching other missions beyond?
Yeah, again, I think right now we've got station officially going to 2020. You know, we're starting to think about what are the advantages of continuing to do research beyond 2020. And I think as you see some of the science described here, you'll see a natural reason that, hey, if you knew you were going to be operating beyond 2020, you might change the way you do your investigation. You might do things a little bit differently. So we're in the process of starting to think about how much we can extend station. The physical hardware is probably good till 2028 or so. So we're trying to figure out when the right time to start talking about that is and start moving forward. So you'll see us start describing and moving things
Okay.
forward.
So we're gonna
All right,
jump
so I think
in
we're
now.
ready to go to the crew here. And this is really special, what you guys are getting to see here. We don't normally do this. We usually get videotape things because we can guarantee those. So live stuff is really risky, so you should really appreciate what you're getting to see here. Yeah. Go ahead, Trey.
We'll let the mission
right.
control get started here in our control room. You guys getting audio?
Please call station for a voice check.
Let's see. Okay. All right. Well, okay, station. This is NASA headquarters. How do you read? Great. Good. I'm gonna take that as a yes.
Headquarters, Space Station has you loud and clear. Welcome aboard.
Fantastic. Great to see you guys. We have a quick word from one of our speakers, and then we'll get started. Please go.
Hey, this is Gerst. Thank you guys for doing this today. You got about 150 folks here in the auditorium. They are excited about station research. They are ready to type out your words and your messages, so have fun with them today. They got great questions for you. Enjoy your interaction with the crowd here at headquarters in the auditorium. Great to see you guys on orbit. Nice to have communications today.
Well, we have a number of guests here with us that have a number of questions, so we'll go ahead and jump into it. Show of hands. We'll start here, right there, and then there. And please stand up.
Hi, this question is for my nephew back home, Thomas. Thomas wants to know how much time would the International Space Station take to perform a collision avoidance maneuver?
Well, you know, used to be that we really had to do a lot of tracking and get ready for these things, and we have this new plan on board where we have a pre-programmed collision avoidance maneuver. What collision avoidance maneuvers essentially do are change the orbital altitude so that we can get more separation between us and the object when it comes through our orbit. So it's just usually a reboost is what we're going to do, and we're down to being able to execute these things in about 6 hours or 7 hours now, with enough warning. So that's really a pretty quick response. There are pre-programmed plans on board to do it, and that's really a great degree of safety that we've added just in the last increment. So it's new, and we like that.
Go.
Hi there. Did you all get a chance to see the meteor, the asteroid that came through last week?
We were pretty excited to read about that, just like everybody on Earth. And so we thought since we're a little bit closer, we'd try and see it. But we're not that much closer. I actually set up a camera in the window that was that our guys in Mission Control told us would be the one with the best view. But even they said it's going to be really faint. But I set up a camera on a time lapse, hoping that we could see the streak of the asteroid going by across the stars. But it was like less than a pixel. We just don't have enough magnification for the cameras on board. So we were looking, but we didn't see it from here. No, unfortunately.
Hi. If a major climate event were ever to break out back on Earth, like a hurricane or a volcanic eruption, would NASA ever call on the astronauts to play a part in taking pictures or doing data collection?
Yeah, they sure would. As a matter of fact, every day we get requests from scientists around the world to look at changing events, weather, geologic events that are relatively quick, such as sedimentary changes in rivers. We get called on to look at those all the time. And so generally, though, we try to squeeze them into our general workday, but we're always excited to have a chance to have this really unique perspective on something, particularly if it's helpful. In the Russian segment, they do the same as well. They've been able to identify places where mudslides, landslides have occurred, and been able to identify even the sources of those. So that's a really good thing about having people up here to pick those things out.
How much oxygen do you use in the space station daily?
That's a really good question. I'm not sure we have the answer to. We of course are using it up. A lot of us. There are 6 of us on board, so we use a fair amount every day, and we have specialists on the ground, our environmental control specialists, who keep track of how much we use, and we have oxygen generation systems on board too to replenish that. So kind of over the course of the day, they take care of it and keep replenishing it. And it's one of those things that, fortunately, as astronauts, we don't really have to worry about too much. We just wake up every morning and our oxygen is right at 21.1%, and our pressure right back here on the gauge is at about 740 millimeters of mercury, and we're good to go. So they have a great plan now. We use a little water to generate oxygen out of that because H2O has water has oxygen in it. We get our oxygen from that. And then we do have some reserve tanks on board if we need them. So that's a great question. I have some homework to do on that one.
That's good.
Okay, I just wanted to thank you guys for this amazing opportunity. Looking at ISS research, what is the most significant discovery you've made with experiments that you did not intend to discover?
Well, I tell you, there are discoveries going on all the time because we're involved in just a subset of the science that's going on here. And we have to pick our favorite things. I like medical research, but there's one, the capillary flow experiment, where we are in contact real time with the scientists that designed it. And we're able to look together. We're actually looking at the experiment, and this has to do with fluid flowing through different chambers they've designed on the ground. And they're able to see it on a video. And both of us together can go, oh, wow, what just happened here? And we go back and look. And they're finding out ways to control tiny bubble flow and to control fluid flow through veins and tubes. And what this allows them to do, and the reason why I think it's so important, is not only are they designing pumpless fuel systems for spacecraft and zero gravity, but it turns out a lot of these engineering principles that they're actually tweaking daily with this experiment, these principles apply to very small amounts of fluid, and so your lab on a chip, your medical diagnostics that use blood and urine flow in little tiny chips, they're able to actually expand the capabilities of these devices to measure things we've never been able to measure before. So you get tinier, smaller medical devices that can go places that they hadn't been able to before.
Sandra here. My question is about the fish that were recently brought up in October on the Soyuz launch that actually brought you, Mr. Ford, up to the space station. What is the status of those fish? Are all 32 still alive up there in their little aquarium? And what other animals does NASA plan to bring up to the space station or has brought up to the space station? And what do we learn from them?
Well, that's a great question. I'm not sure you're going to love the answer, but it's a good one anyway for science. We brought up 32 fish with us on Soyuz 32S. Some of them have already gone home, and the rest of them are in a freezer already. What we did with those fish was during phases of their lifetime and their duration on space station, just like us, they have bones that create and destroy, well, they have a system that creates and destroys bone, the osteoclasts and osteoblasts, just like mammals have. And since we're mammals, this is very relevant to the bone loss and bone production that we have as humans. What we have on space station is very different. It's more like bed rest patients. So by looking at these fish in the zero gravity environment, they're able to see the mechanisms with which their bone is created and destroyed. And that was a very important thing. But what we had to do then is fix these fish at various stages in their development. So it was a very humane way of doing it, but we took the fish out. We actually pulled them out of the aquarium, some of them immediately after we arrived on board, and some of them months later. And then these fish will go home as samples for the scientists to study. So these fish gave their life for science. Most of them will go home again with us on Soyuz 32S, and we are very much looking forward to the results. Could be really significant findings to help out with things like osteoporosis in elderly people. And of course, astronauts too in the zero gravity environment. So a very important study.
So you guys went up there very fit. How does it feel as your body changes during weightlessness? And when do you think fat people will be able to go to space?
it's all of us have been lucky enough to fly before this long duration flight. I think everyone would agree that the process by which our bodies adapt to weightlessness, you can feel it. And you can see how your body is changing. It's really rapid for the first week or two, almost day to day, as the fluid shifts, as your balance system changes and relates to how you see things, how coordinated you are in weightlessness. You're pretty clumsy when you get up here, but after a while, maybe sort of like a young ape swinging through the jungle, reaching out for vines, we get used to it, and you get pretty graceful in weightlessness as you adapt. But it definitely takes time. We also lose a little weight, but mostly it's just water, because there's no fluids pooling in the lower part of our body that our body's constantly pumping up to our head. Our legs get really skinny up here because gravity's not pushing the fluids down to our legs. And to live on a space station, you have to pass a really hard physical, just because we can't afford to get sick up here. We really want to have healthy people. But we're trying to open the doors to space to everybody. That's the whole purpose of this, is figuring out how to safely get to space and back again. And just like early in aviation, at first it wasn't for everybody, and it was only a very select few could fly. And now, of course, pretty much anybody can fly anywhere around the world. And we're just in the early stages of that. We haven't invented everything we need to invent yet. But hopefully soon, everyone will be able to get this incredible experience that we're lucky enough to be part of.
Hi, my name's Ray. This is really cool. You guys are growing plants up there, and I'm kind of interested in how you're doing that. And also, we were told that there is change in gene expression in those plants. Wondering if you could elaborate a little bit on that. Thanks.
For sure. We've grown plants up here in the Mir Space Station and here on the ISS. Not aware of one going on currently while we're on board. But while I'm not aware of the results of those plants have come back, and cuts from them have come back. And I'm not aware of the results of the gene expression on those. But some studies have shown that it's really fascinating. The plants have a way of extending their roots and doing it very well without gravity. So gravity does not seem to be a factor in that. Not only that, but you can see gene expression pretty quickly, just like in mammals. Just in even minutes with a new environment, you can start to see changes in gene expression. So, and how they do it, that's the fascinating thing. I wish I knew more about it, because it's quite an engineering problem to supply all the nutrients to the plants, get rid of all the waste products that you need to, and still have healthy, viable plants. We got a lot of smart people that are able to work that out.
Hey guys, how are you out in space? It's nice here. How much time do you have off the clock, so to speak, to do personal experiments, draw, sketch, personal fulfilling things?
We have a very busy life up here, to be quite honest with you. The work week is pretty full. We joke a lot, but it really feels true. There are 2 days of the week. There's Monday, and then but it just goes by, and then it's Friday, and then the weekend goes by, and it's Monday again. And we have no lack of things to do. I've been up here for probably almost 120 days, and I've never not had something else that I wanted to get to as soon as I was done doing the thing I was working on. So it's just really an incredibly busy place. We do have weekends free, and we have tasks lists of things that we can do to help Mission Control out to get a good start on the week. And we try to do a fair amount of that. We clean the module and stuff on the weekends as well. And we exercise 2.5 hours every day, even on the weekends. So all that stuff adds up to a significant amount of time, just maintaining our health and fitness and maintaining the space station complex. But we do have slivers of time, and we all have projects we bring up. I have my little red book. Sometimes we don't show it to other people because we don't want other astronauts to steal our ideas. But when I go home, if I haven't had a chance to do all the things I wanted to do, I'm going to pass it on to these guys and let them try it out too. But there are just, you probably have a lot of ideas of things you'd like to try up here. I'm an attitude dynamics guy. That's kind of what I studied as a grad student. And there are some things I want to do to demonstrate some things that I think you can only demonstrate in space. And I've already made a few tapes about some attitude dynamics and things just and sent to the ground as personal ones that I'll edit post-flight. And of course, there are things we just like trying to do as well. Sometimes on a Friday night, for example, when we don't have to worry about the next day usually, we'll get back in Node 1 at dinner time and we'll try things. We'll do water experiments and water bubbles and try to capture them or move them around and just try various things that we find interesting to us. So we do have some spare time to play in space, and we can thank Mr. Gerstenmaier for giving us those little slivers up here to enjoy the place too. And of course, we do a lot of photography out the windows. It is almost impossible to pull yourself away from the window. The cupola is just gorgeous. The Russians have some windows too that are very high quality windows to look out and take photos out. And every time you go to them, there's something there that just sucks you in. And once you just want to stay there at that window and not go away. And so that's what we do with our spare time. It's a little bit like being in a dreamland up here, frankly. Every day is like a dream, and I know I'm going to wake up in 4 or 5 weeks and go, was I really there? I can't believe I was really there and in zero gravity. I'm really in zero gravity, so you check it out. So it's a pretty fun place to be, and we do have a good time up here.
Hi, this is probably the coolest day of my life. I just wanted to know, you spoke out the window and all the pictures you've taken. What's probably your favorite time to look out the window and one of your favorite pictures you've ever taken?
I don't think I have a favorite time to look out the window. You know, I was at the window with Tom the other day, and it occurred to me my favorite time as a crew is when two of us are looking out the window, because it's as if the two of you are almost looking at a miracle together. It's just so brain-stoppingly beautiful to come out of this, what looks like kind of an austere hospital-like laboratory, and suddenly you poke your heads into this little room, and there's the whole world just pouring by underneath you, and it's been there the whole time. And we only get a little bit of time every day that we can go steal and spend time there. But to be able to share that is magnificent.
Okay, we're gonna try to reconnect here in just a moment. So I'll give it a sec. Okay, looks like we have it back. We hear you. Go, go, go. All right, let's go ahead and take last question.
Okay, go ahead. How do you use math in space?
Sorry, could you repeat the question, please? We didn't hear it.
How do you use math in space?
How do we use math in space? Gosh, we use it all the time. We use it for simple stuff. We grow when we come to space. So we actually have a place on the wall over here where we measure how much we grew, because our backbones stretch a little bit. We don't really grow, we just stretch because gravity's not squishing us. But we measure how tall we are. We use math to try and find the spaceship when we fly up here to rendezvous and dock. And it's like a big triangle the whole time between the Earth and the other spaceship and us. And we're constantly doing the trigonometry, the Pythagorean theorem, the square of the hypotenuse and all that to figure out where we're going to go next. We use it just for calculating speeds and measures here all the time. We're emptying one tank and filling up another tank. And some of the math is pretty complicated for a rendezvous. Some of it's very simple, just to see how tall we are today.
So gentlemen, before we lose you, we have one of your colleagues here who's going to be speaking to us next, and just wanted to give him a quick opportunity to say goodbye to you. Don?
Hey, this is Don Pettit. I'm jealous that I'm down here and you're up there.
All right. So thank you for answering our questions. We really do appreciate it, and best of luck up there. Thank you.
Well, thanks. It's great to hear Don's voice on the ground too. He left a legacy up here. A lot of his equipment he brought up here is still on the walls, and we just try to live up to Don's high standards and learn all we can up here. Nice working with you guys today. Have a great day.
Thank you.
Station, this is Houston ACR. Thank you. That concludes the event.
Sounds good. All right. Gonna go ahead and introduce Don while the guys have fun. All right, sounds good. So our next guest, astronaut Don Pettit, is a veteran of 3 space flights, having logged more than 370 days in space, over 13 hours of spacewalks. He was selected as an astronaut by NASA in 1996. He lived aboard the International Space Station for 5.5 months during Expedition 6, was a member of the STS-126 mission of the Space Shuttle Endeavour, and again lived aboard the station for 6.5 months as part of the Expedition 30 and 31 crew. For those of you who didn't see him perhaps catch the first SpaceX Dragon that resupplied the space station back in May, you may recognize him, for those of you who have Angry Birds Space on your smartphone. When you click on the International Space Station logo, it's a video of Don that pops up teaching you about microgravity. So please help me give a warm NASA Social welcome to astronaut Dr. Don Pettit.
I've got some techno stories to tell you, although I'm told that I only have 5 minutes to actually talk and then questions, so maybe not techno stories, but a techno story. So could I get the first slide? And it has to do with one of my favorite pastimes, and that's drinking coffee. Okay, next slide. There. Okay. So you can imagine if you have a glass, and like a coffee mug or something like that, it just doesn't work in a weightless environment. The coffee stays in the bottom, has a hemispherical concaved surface, and it just stays in the bottom of the cup. And you tip it up and it still stays there, it won't pour out. And then when you move the cup, the surface tension isn't strong enough to actually hold it in there, and it'll splash out and make a big mess. So not only can you not drink it, but you end up making a big mess. So the engineers at NASA have come up with a really cool way to have your coffee. It's called a drink bag. And this is Kona coffee, one of my favorites. If I had a straw and a way to inject water in it, I'd probably be drinking it in front of you right now. But there's a little bit of instant coffee in here. You squirt hot water into this thing, put in a little straw, and you can suck your coffee from a bag, just like all you kids do with those little juice boxes. And I'm not sure which came first, the juice box or the NASA drink beverage bag. But anyway, it's kind of a gauche way to drink your fluids, but it's a perfectly fine engineering way to get your beverages when you're in a weightless environment. And so here you see a picture where I've got a bag, a Kona coffee, just like this, and above me there is our beverage machine. I call it the galley. And it's basically a hot water, cold, or I should say room temperature water machine that can inject either room temperature water or hot water into one of these bags so that you can drink your bag of coffee. Now, when you leave Earth, you are leaving the zone of water. We talk about water shortages here on Earth, and really on the planet, there is no such thing as a shortage of water. There may be a shortage of potable water in certain locations. There may be a shortage of water you could use for irrigation in certain locations. But on a planetary scale, there is no shortage of water, and you don't really know the meaning of a desert until you leave the planet. And then you find out what it means to not have a bunch of water with you. And so, human beings liking to drink their coffee, we need to have a source of water. So there's our galley machine, which squirts out all this nice, clean, potable water, either room temperature or cold, or room temperature or hot. But where does the water come from? that runs that machine. Next slide, please. Well, it comes from some refrigerator, upright freezer chest kind of size pieces of equipment. And this is one of those pieces of equipment, a picture taken inside. And here you have all kinds of pumps and filters and things like that, which can help purify the water so that it's fit to drink. But where does the water come from that goes into this machine? Next slide, please. It comes from this machine. And this machine, it's a still. Now, it's not a moonshine still. We refer to it, even though in space there's moonshine, right? But it's not the kind of moonshine you're thinking of. It's real moonshine, and this is not just a still. We call it a distillation unit. And it's a lot like distillation on the ground, but distillation involves bubbles and vapor and liquids and separation, and it's all due to gravitational buoyancy forces. So in order to distill something in a weightless environment, you have to have rotating machinery, which creates an angular acceleration, which is a fancy way it makes its own gravity, and then vapor and liquid and droplets in gas and things like that can separate out, and you can run a distillation outfit in a weightless environment. And this is our machine for doing that. When it flew up, it actually came up on STS-126. We brought it up on our space shuttle. It was serial number 001. And it ran for a couple of days, and then it broke. And we actually flew it back down with us on STS-126. And then the NASA engineers sharpened their pencils. They figured out what the issue was. We flew it back up. And we've had some wiggles with this piece of equipment. It's a complicated piece of equipment. It's serial number 001. But we've got the bugs worked out. And this thing has been running for years now as a distillation outfit, making water that goes into the filter system, which then goes into our galley, which ends up making coffee for us in the morning. So where does the water come from that goes into this distillation outfit? Next slide, please. It comes, now you see, it takes technology for human beings to go into frontiers these days. Used to be, if you wanted to go to a frontier, you just walk west. If you had a horse, you could ride the horse, and you just figure out what to do when you went there. Nowadays, frontiers are bottom of the ocean, a high altitude flight or high altitude mountains, going into space, under the stage of a microscope, through the eyepiece of a telescope. These are the frontiers now that human beings can explore, and it takes equipment to go on these frontiers. And it takes equipment because we're going places that human beings were not meant to be. And the only way we can go there is to take pieces of equipment that provide us shade so that we can live there. And to make this equipment, it takes engineering, and you need to have a little bit of math to do the engineering. You need to have the science that goes behind all of that. So that way you can have all this equipment that will allow you to live in these frontiers, which is why I tell students that in order to do what I do for a living, you need to know math, you need to know science, you need to know engineering, because you have to take care of the machines that allows you to live in the environment that you're in, and this frontier happens to be space. So anyway, this menagerie of tubes and pumps and separators, this is in this piece of equipment, and it separates liquid from gas. So there's a fan there that sucks in a lot of air, there's liquid in the air, and this machine separates the liquid from the gas, and then it shoots the liquid into that distillation outfit that you saw. So where does the water come from that goes into this air-gas separator? Any ideas? Next slide we'll see. Now this is not our galley, this is our toilet. And what I've been describing here is what we refer to as a regenerative life support system. Because remember, we're going off into this desert, not just a desert here on Earth, but the desert of space, where you can't even find water. So you got to take the water that you already got with you, and you got to figure out how to separate out the nasty stuff from the good stuff, and then you recycle the good stuff. and we call that our potable water. And you can see here, this is part of our zero gravity space toilet, and that funnel thing, that bright yellow thing, that's collects the urine. Now, when I took this picture, I sent it down to my family, and I told my boys, this is a sunflower. And I got an email back, and they said, no, this is not a sunflower, it's a peony. So someone asked about plants in space. Well, this is a different kind of plant. So again, what I've showed here is our regenerative life support system, part of it, where we start off with urine, goes into air urine separator. The urine goes into this fractional distillation equipment. The bad stuff goes in one container. The good stuff goes in another direction, goes through a bunch of filters into the galley, and then you can make a bag of coffee with it. And the NASA engineers call this regenerative life support system, but that doesn't, to me, connote what it really does. I like to refer to it as the coffee machine, because it can take yesterday's coffee and turn it into today's coffee. So with that, that was my 5-minute spiel that was probably more like 8 minutes. Sorry about the stories. I've got lots of techno stories to talk about. I only had time for one. Let's open it up for questions, and maybe the questions will let me go into another story or two.
Yeah, Don, you want to call him?
Yes, there's a fellow right there with his hand up. Ask me a question.
Hi, my name's Aiden, and I have a question. What are they growing on the ISS right now?
What are they growing on the ISS right now? Well, we have experiments where we grow things, and I think right now they're in between plant growth experiments. When I was there, I was growing some garden vegetables. I grew zucchinis and sunflowers and broccoli, and I actually started to write a little dialogue, a little blog called Diary of a Space Zucchini. And then one of my colleagues made a Twitter account for Space Zucchini. And the last time I checked, Space Zucchini had more followers than I did. So that was what was going on during Expedition 3031 when I was on Space Station. However, there are always clandestine growth experiments on Space Station because we have trouble with molds and smuts and things like that, which is one of the things we do on Saturday is we get out our little cleaning agent and we clean up all the little powdery mildew stains and the little green algae stuff growing on the side and things like that, because just like here on Earth, you will have all these kind of unintentional and unwanted things that grow in your house, and we all have to work to keep these seeds cleaned up. Okay, next question.
Could you maybe just talk about maybe the physical rehab that you have to do coming back to Earth and how you get used to Earth's gravity again after being in space so long?
Okay, physical rehab. Coming back to Earth is more provocative than going from Earth into an orbital environment, most definitely. And you are strong. We're actually physically stronger when we come home than when we launch. A part of it is exercising for 2.5 hours every day, because how many people in the middle of your career do you get to exercise 2.5 hours, hardcore exercise, weightlifting and hardcore cardiovascular exercise? Most people don't do that for 2.5 hours every day if they're actively working at some other job other than working out for 2.5 hours every day. And so when we come back, we are in really good physical shape. However, it takes a while for your body to get used to gravity again. You have some control issues. And here's one example that I found fascinating. If you hold your arm out now, you don't feel the weight of your arm, but you feel the weight of this bottle of water. your brain acts like an electronic scale, a laboratory electronic scale that tears out the weight of the beaker and only weighs what's in the beaker. And so by tearing out or zeroing out the weight of the beaker, then you know the weight of the stuff that you put in it. And so your brain is tearing out the weight of your arm. It's a no factor, and you feel the weight that you hold in your arm. And your brain does this automatically, and you don't even know that it's happening. You hold your leg up, you really don't feel the weight of your leg. When you come back to Earth, your brain stops doing that because it hasn't had to do that for the last 6 months. And so you hold your arm out, and now you feel the real weight of your arm, and it feels heavy because you're not used to feeling that. You hold your leg out, and it's like, whoa, my leg weighs 1,000,000 pounds. And you bend your head over like that, and it feels like somebody's stacking a lead weight on the back of your head because your body isn't used, your brain isn't used to subtract out the weight, the effective weight of its own brain. And it takes maybe 10 or 12 hours for this algorithm to get kicked back in again. So that's one of the surprising things I found when I came back to Earth, is this electronic scale aspect of your brain and how it tears out the weight of your limbs so that you only feel the water in it. Next question.
Hi, Don. I'm working on the Windows on Earth project you may or may not be aware of. It's to help you guys track your photo locations right from the cupola. And part of what I learned about actually just recently, you invented a whole new machine to actually do night photography. And I think it'd be pretty amazing to see kind of how you had to go through that process.
Okay, this was the tracking machine that I made on Expedition 6 out of junk and spare parts found on station. And the orbital motion is pretty fast. And if you take a picture with cameras that were state-of-the-art at that time of Earth at nighttime, you would just have blurry streaks, just because the exposures were around 1/2 to 1.5 seconds. And there's enough orbital motion during that time to make everything just blurry. And so I cobbled up this machine out of junk that would compensate for the orbital motion so that you could stay on target for maybe 2 seconds and you could get a couple of pictures off without having the orbital motion make it blurry. And central to this machine was a long threaded bolt that I found on the Russian Progress space vehicle. And since that vehicle ends up burning up in the atmosphere, I figured that they wouldn't miss just one bolt. Right? So I lifted this bolt from the Progress vehicle, nice bolt about yay long, and then I could turn that with one of our drill drivers, and it would push against the platform and precisely move the camera mechanism because of the threaded bolt pushing against the platform, so that way you could compensate for the orbital motion. It was all done manually. And it allowed a whole series of pictures, thousands of pictures taken all over Earth of cities at night. Now, fast forward to around 2010, cameras have improved so much now that you can take pretty decent pictures of Earth at night without having to use this mechanism. And the European Space Agency, ESA, made a really nice computer version of this mechanism that you can dial in your orbital altitude, things like that, and it will automatically compensate for your orbital motion. You can mount a camera to it, and they call that the Night Pod. And that actually flew up with Andrei Kuipers, Oleg Kononenko, and I when we launched in our Soyuz for the beginning of Expedition 30. And we used that on station, and with that machine, you can take amazing pictures of cities at night now or any other nighttime view of Earth because it will track and basically cancel out the orbital motion for the duration of the exposure. Yes?
Hi. A lot of science is counterintuitive, and I was wondering if you recall anything where you had to kind of get your head around because it wasn't what you expected.
intuition, particularly technical intuition, is one of my favorite subjects, and which I believe is one reason why we as human beings like to go to frontiers, because we are used to living here in our little cities and suburbs, and we've got sidewalks, and we have grocery stores, and everything operates in a well-known manner. And then you go to the bottom of the ocean, or you go into the stratosphere, or you go into space, and all of a sudden things don't work the way that you are pre-programmed, your intuition, your experience thinks that they should be working, and that makes an environment that's rich for discovery. And I think that's part of the reason why human beings like to go into frontiers. One, it's cool, but two, it's a fascinating environment, rich for discovery, and in the long run, this is what makes our society affluent. This is why we have the standard of living that we do right now, is because people in the past did exploration and they learned new things. So the idea that you go someplace where your intuition no longer applies, that's the whole point of going into space right now. And every day I would see something that would just make my jaw drop, because it ain't supposed to work that way. But it does, and that's because we are in this amazing environment. And just a couple examples. One is to make a large sphere of water. And we've all seen spheres of water in space, you know, little spheres, maybe an inch in diameter. I'd make a sphere the size of my head. And for the only reason of, I know that the ratio of surface tension force to inertial force will decrease as the sphere gets larger and larger and larger, which basically is a fancy way of saying that the role of surface tension becomes smaller as the sphere gets larger, and other things will dominate its behavior. And so I made this big sphere of water just to see what might happen. And so you'd make this big sphere of water, and then you'd puff on it. And then you'd squirt water at it. And you'd do whatever you think might be fun to do to this big sphere of water, and you would observe its behavior. And I found just watching this big sphere of water to be a jaw-dropping experience. Yes?
Do all solids stay solid in space?
Do solids stay solid in space? Yes. And the reason they do that is because of this big word that we have. It's called thermodynamics, which if you go into engineering, you'll probably have more classes in that than you would care to have. Thermodynamics is not known as to be one of the more exciting classes to sit in a college lecture. However, the stuff you learn in that class you will use every day as an engineer. But anyway, getting back to solids. A solid, it's a material property, and unless you somehow transcend its melting point, either through temperature or pressure, it will stay a solid. So by virtue of going into a weightless environment, solids will still remain a solid unless you change its temperature beyond its melting point, or you increase the pressure, which will cause it to melt, which is why we can ice skate, because you have a layer of ice and you have ice skates. By getting on the ice skate, the blade of the ice skate is so narrow with your body weight, it increases the pressure right at the contact zone, and it melts the water. So when you're ice skating, you're really sliding on a little film of water. Next question.
For one more question.
Okay, I have a group of middle schoolers in the Bronx who would really like to know, what is your favorite science in microgravity?
What is my favorite science? Well, that's kind of like asking what is your favorite movie or what is your favorite food. It kind of depends on your mood. Right now, one of the favorite things that I did on Expedition 30, and this is off-duty science of opportunity pastimes, and that was figuring out how to raise plants without having a formal science experiment out of it, without having a big incubator, terrarium with power and all this stuff, but just the equivalent of a potted plant in the corner of the room that you dribble a little water on every day. And the sole purpose is just so you have a little bit of greenery to look at, because we're human beings and we're living in this machine environment, and it's nice to have something other than your crewmates that are living examples of what it was like to be on Earth. And so raising space zucchini and space broccoli and space sunflower were one of my favorite pastimes on this last mission. And trying to figure out how to do it when you don't have any dirt and you don't have any nutrients, and all you had to start off with were a couple of seeds. And what I found that I was able to do was to take food, little leftover food things, and I could compost it. I'd make my own compost, and then, which is just a fancy way of saying that you let your food spoil. And then you take the juices from that compost, which I referred to as tea, and then I would aeroponically, aeroponics is different than hydroponics, and aeroponics is something that NASA has been a big instigator in researching that topic. But I would use aeroponics with this compost tea taken from our spoiled food products and use that as the nutrient base to grow the plants.
Please help me give big thanks to Don Pettit. Thank you so much, Don. Appreciate it. Thank you. Okay, our next guest is going to help us better understand some of the really staggering number of parallel investigations happening on station at all times, and the benefits in particular that we get from that research. Dr. Tara Rutley is Associate International Space Station Program Scientist from NASA's Johnson Space Center in Houston. In this capacity, she represents all aspects of NASA science on the space station. This includes coordination of experiments with scientists and international partners and communicating information about the experiments and results to the public. She's also an aquanaut, for those that don't know, having served as an engineer on one of the NASA Extreme Environment Mission Operations crews, NEMO 6 to be exact, where she lived and conducted research in an underwater habitat as an analog for space exploration. Please help me welcome Dr. Tara Rutley.
Hey, thanks guys. It's really fun to be here. First things first, science is fun. And that's why I'm here, right? And that's why you're here. That's why we're all loving NASA. And so I guess we'll get started with the first slide. Let's see. So I hail from @ISS_research. That's my office where we tweet in 140 characters or less the best science that happens on the station every day. So you should definitely keep up with us. If you're not, now you are. And I work in the Space Station Program Science Office out at Johnson Space Center. And it is our job to keep up with the science that's happening on station and communicate it to you guys. And so I'm here to talk today about some of the benefits that I think are going to resonate with you all, because I bet you, like any other American, are interested in what we're doing on station and why we do it and what we're getting out of it. So that's what I'm here to share with you today. So we'll go to the next slide, please. What kind of benefits come from research in space? Well, that's a loaded question. And the first thing we all have to remember is science takes time. It's a little bit of a different culture here at NASA when we're used to these shuttle launches with the fire and the attention with every launch as a major milestone. So now we have this orbiting laboratory on orbit. And it's a little bit, it has its peaks and valleys in terms of the really cool stuff that's going on. For me, I think it's cool all the time. But it's a laboratory unlike anything else on Earth. In fact, there is nothing like it even on Earth. There's nowhere that you would find any kind of laboratory that would share material sciences facilities with life sciences facilities, with plants and humans. And so the challenge in itself being interdisciplinary is the first challenge. But we get it done, and we get a lot of science done. In fact, the crew that you just saw on orbit has done the most science in the history, I think, of station to date. So they're very, very busy with all the research that they're doing up there. And that's the purpose of the space station. It's to do research so we can learn how to better ourselves here on Earth and how to get us to the next step beyond low Earth orbit. So the way that our brains can kind of get our minds around kind of categorizing some of the cool stuff that comes from the station research are in three categories we like to discuss. The first being advancement of scientific discoveries. We as human beings we have a thirst for knowledge. We like to advance the textbooks. We like to figure out where we come from, where we fit into the big picture. And there's a lot of discovery science that's happening on station. And I'll share some of those with you today, too. there's a lot of Earth benefits that are coming from the work we're doing on station. Anywhere from advancements in telemedicine to the robotic surgery, brain surgery that you see in the image here. That was a derivative of the Canadarm. These are all things that we even talk about vaccine development. There are things that benefit you that come from the research that we do on station. And then lastly, we like to speak in terms of space exploration benefits. So some investigations that we do may be solely for the benefit of getting us to space and getting us further beyond low Earth orbit. And that's cool too. So we've got 3 major categories that we keep up with, and I'm going to share some of the results and benefits with you guys today. Next slide, please. So what are we doing on ISS today? The first thing I want to share with you is the staggering number of investigations that are happening in a 6-month period. So when you see investigation 33, 34, that spans about 6 months. That's the increment, and that's what these guys here on orbit, we're in increment 34 right now, or expedition 34. I had no idea when I came to work for the space station program 4 years ago that we were doing this many investigations. In fact, we weren't. We've ramped up in the last 4 years, but at any one given 6-month period, this crew is doing about 165 different investigations. And it doesn't mean that they're all doing them hands-on. Some of these are automated. Some of these are controlled from the ground. Some of these just kind of run in the background. But at any rate, they represent, that crew up there of 6, represent about 400 scientists on the ground. So it's a staggering amount of data that's coming back supporting scientists around the world. And we do investigations across all disciplines that you can think of, anything that would be affected by gravity or that you need Earth or space components to see can be done on station. And we also have, not only is it multidisciplinary, but we do it for we have different goals, right? So you probably heard of the National Lab component, which allows anyone other than NASA to have access to the space station as the unique platform that it is to drive the science that's happening. And the real goal of the National Laboratory effort is purposefully Earth benefits. And so now anything we do here at NASA, most of the funding is for human exploration. We'll get Earth benefits from that too, but the primary goal is to drive exploration. And so in terms of Earth benefits, there's a whole lot being done in bio and biotech that spreads across both Earth and space exploration. There's a whole lot of human research being done in the exploration realm because, let's face it, you've heard a little bit today and you'll hear from Marshall Porterfield next. The human body has a lot of challenges to overcome before we get to low Earth orbit because a lot happens to the body to get beyond low Earth orbit. A lot happens to the body just in low Earth orbit. We do a lot of physical sciences. We do a lot of tech demos, tech demonstrations, as you heard from Mr. Gerstenmaier, Robonaut, the Bigelow device or module that's going up, human robotic interactions controlling from the ground, communication delay scenarios, advanced ECLIS systems. All those you want to send up to space station to use that space station as the technology test bed that's going to drive us to go to the next step. Astrophysics, anybody here familiar with the alpha magnetic spectrometer? That's the celebrity, but there are more on orbit as well. Earth sciences benefits Earth, benefits to space exploration quite as well. And of course, education spans across just about everything that the space station program participates in, whether it's research or the students participating in research on orbit through the astronauts or designing hardware and things. So we go cross-disciplinary, and there's a lot going on even right now. Those guys on orbit you just talked to are busy getting back to work. So next slide, please. So the first bit of discovery I want to share with you guys comes from a payload that sits on the outside of the Kibo laboratory. It's managed by our Japanese partners, and it's called the MAXI payload. And it can scan the sky. I think it can do a full sky scan for X-ray sources in about an hour and a half's time. And so that's the advantage of sitting on space station is it can get full sky images, unlike some of the unmanned satellites that take a little bit more time to do. What you're looking at is on the top right corner is just an image of the sky during a quiet time, and then on the right you see a big bright yellow blast, and it's just an example of a new nova that the MAXI payload found, just advancing some of the basic, some of the scientific discoveries in the field of astrophysics. But the big thing I wanted to share with you guys today is the nice pretty picture, which is an artist rendition of what MAXI and the NASA SWIFT satellite picked up on a few years ago. when they noticed an X-ray source change. And what they determined by putting both teams together, they had enough statistical power to get their data to agree that they were seeing the first time ever a black hole shredding a star that orbited a little too closely. And so it's something astrophysicists had theorized, had never really seen before, especially real time. We call this real time, but that was 3.9 billion light years away. And so what Maxey and Swift picked up on was this X-ray jet that came shooting out of the center of the black hole as this star was actually being shredded. So something that turned up in the Journal of Nature. It was published in the Journal of Nature, which was a big deal for scientists. And so the Space Station program is excited about this scientific discovery, advancing a little astrophysics, and sharing it through the Journal of Nature. Next slide, please. A little bit about exploration. I think most of you in here are familiar with the little guy here on the image, this Mars Curiosity rover. Well, there's a link between station and some of the work that's being done on Mars right now, and one of those has to do with some of the materials research we do on ISS. So in the top right corner is an image of a payload called MISSE, M-I-S-S-E. And it's basically a box platform that sits on the outside of the station truss, and it's full of different types of materials and paints and coatings. And it sits out there because we want to see what happens to it as it's exposed to the harsh environment of space. Ultraviolet radiation, atomic oxygen, thermal swings, debris. And so when these samples come back, the scientists can analyze what's going on with these types of samples and whether they're useful for spacecraft design and future development. Well, we found out on the second MISSE 2, that there was a paint that was on that platform that was able to survive the harsh environment of space, and it's electrically conductive, so it can dissipate static electricity that a device might experience in an environment such as Mars when you get to high radiation environments. So because that paint survived the harsh environment on station, it was used to coat the major power supplies of the Mars Curiosity rover. And so now it's an example of something that we've used on station and been able to apply it to our future exploration just as we are here on Mars. Next slide, please. And something that we can all resonate with in this audience are of course the Earth benefits. And we feel like that we can resonate most with understanding the health benefits that come from station, the Earth observation and disaster response. You heard a little bit about that today, and the education. With regard to health, some of my favorites that I like to talk about, but I don't have a lot of time, but I'll take questions, is some of the streamlining in R&D for vaccine development. Some microbes just get on orbit and get in the environment of microgravity and just behave differently. And we can leverage the way they behave to help us drive vaccine development and pharmaceutical developments. Some advancements from health as well. Some innovative ultrasound techniques that have come from training our crew on orbit and talking them through some of the ultrasound sessions have been applicable to those of us here on Earth. And when we do telemedicine using devices in areas in remote locations, we can help talk these non-users, basically, of ultrasound devices to be proficient at their own imaging across the world. Let's see, Earth observation. You heard a whole lot about Earth observation today, both from the crew and from Don. Basically, our crew, there are devices there to observe the Earth that are automated and controlled from the ground, and a mix of the crew taking photos directly. And the imagery that we get from the crew, there's nothing that beats real time talking to the crew, telling them the next time you pass over, we need an image of this volcano or this tsunami. But there are also, lighting effects. The space station can pass over different landmarks at different points of the day and get you different lighting effects over different areas as well. Automated responses and non-crew tended get you a whole lot too, so that you can get automated data at any time you need as well, and you can share the images around the world. We look at things like changes in climate, population growth, agricultural changes. You can imagine that we can see it. And then education, of course. The space station program, since its beginning, we have touched just nationally here in the U.S. about 35 million students, whether they've participated in research hands-on, whether they've created hardware that's gone to station, whether they've participated in competitions on orbit, or even talked to the crew directly. And then globally, we've reached about 42 million students. STEM is a big driver. I mean, I was a child of lots of NASA outreach programs, and so I think, and judging from the audience here, we've got some as well. So education is a big component of Space Station, and it's certainly one we take seriously. And I think one last chart I want to share is one that you all will be very interested in, is all the digital ways that you can find us, right? This crowd can pull it up right now. Our office maintains the ISS Research and Technology website. It's a really cool website. We'll list all the investigations that are happening on station, what they mean, some of the results, images, stories about it, all at ISS-Science, benefits and even opportunities. So some of the benefits that I talked about today are just barely touching the surface. And so if you go there, you can find more. There's our Twitter account. And we also have a really cool blog. It kind of brings the science to life. And it's written either by us in the office or by the scientists themselves or by the crew members who have participated in the science. And so a Lab Aloft, you can go there and find out how to bring that science alive. And we share that with you as well. So with that, I think I should take some questions.
Yep, let's take first one here on the left.
Hi, my name is Ori, and you talk a lot about the sort of more the hard physical sciences.
Mm-hmm.
Do you do psychological experiments while they're up there to test mental stresses as they go on their way further and further?
Yeah, the word psychological experiments sound a little odd. But they do. The crew participates in writing up journals. There are investigations that study cognitive function and things like effects of sleep loss on work and on fatigue and work. So there's a number of them, and they're all some of them are retrospective, some of them are active right now, but there's a whole lot going on with that. And of course, as you all know, the crew is very much rigorously psychologically evaluated before going on orbit, so they can kind of tease out some of the issues that they might experience in the closed environment on orbit. Yep.
My name is Lucy Williams, and in the context of using the ISS as a technology testbed, I was curious as to any 3D printing in space experiments that are happening.
Yeah, we are evaluating that.
Also related to basically the inflatable module mentioned before and cargo supply ships.
Yeah, that's a really good question. We are looking at a 3D printer proposal. I think right now, we're in the early stages of identifying one and getting it ready for flight, right? So 3D printing would be really cool to have on orbit. That'd be exciting.
Yes. Hi. I was wondering if you could tell us a little bit more about the NASA NEEMO expeditions and how training underwater and here on Earth can help prepare astronauts for work on the ISS.
Yeah, good question. It's NEEMO. It's an underwater analog that it simulates a closed environment or extreme environment, something similar to what you might experience on orbit. I did NEEMO 6. That was back in, I think, 2004. I was an aquanaut, so I was an engineer at the time, along with 3 astronauts. So I was the only non-astronaut. And our goal was we took up a bunch of different engineering evaluations that we wanted to put in an environment that we started from beginning to end, from design to end user testing for 10 days. We lived underwater in a habitat 65 feet deep. And what it does for the crew is it trains them on crew interaction, what to expect, how to interact as a team, especially against challenges in an extreme environment where 65 feet deep over 10 days, you just can't come home. It's just like something similar to station. So there's a decompression profile and things. So for the crew, it's excellent crew training. For the scientists and the engineers, what I was, it's a great test bed to design something and spend time with the crew testing it out and finding out what works and what doesn't work on the hardware. And I tell you, as a young engineer, I left that mission never the same. It really taught me, wow, when I design something and I'm the end user and I'm experiencing it with the end user, Yeah, it made me really think about my designs and the way I even down to the drawing. It had a great impact on me early on in my career. And I think we're up to Nemo 13. I think they completed Nemo 13. And the missions have progressed from when I was part of it to more exploration. And they've done some really cool stuff. So if you're interested in that, I think it's NEEMO. If you Google that, you'll find all the relative stuff to Nemo.
All right.
Hi, I'm Sharif Jackson, and I'm really curious as to how much time is spent on the safety and the quality control side versus like the actual application of the hardware and software.
It's a really good question. So my background is engineering and science. So I spent about 8 years in engineering before I came to the science world, and that was my life. Ensuring that every piece of hardware that we built was quality controlled and safely managed and produced and delivered to station. And it's, you know, what you see, you may see a piece of hardware this big, there will be a room full of binders, you know, associated with documenting every single step you took to develop that hardware. They're at the very high level, there are safety teams that start very high and it trickles all through the culture, all the way down to the hardware development. And you know, sometimes the engineers and the safety folks, they don't see eye to eye, and that's okay. It drives out lots more questions and lots more answers. And so safety was the biggest part of my challenges in engineering, and for a good reason. You know, right? It's a very delicate laboratory that we have up there, and it's the culture of NASA all across the board to be safe.
On your back left.
Hi, this is on behalf of one of my students in Flower Mound, Texas. What is one of the more surprising or unexpected results you've gotten from an experiment on this ISS?
Good question. Is it okay that if I say that one of the coolest things I saw has come from a student-designed experiment? Really? You know, there's the serious stuff as well, but one of the coolest things I saw, you guys, if you've ever taken like a balloon and you've charged it up and you put it next to that stream of running water and you can, you know, the polarity, you can cause that water to bend towards the balloon on Earth. Well, a student group tried that in space, and you know, the astronauts charged up a piece of tube, let a water droplet go to the tube and to see what would happen. And what actually started happening was the drop started orbiting the tube rather than going to it or away. It just stayed in an orbit. And you know, we kind of were like, we all saw that. We thought that was so cool. And then we, you know, spread around NASA, and you know, management thought that was cool. And so so I thought it was a really cool thing to see that water droplet orbit. And so if you haven't tried it at home, you should try it. You won't get it to orbit. But.
Show of hands, just make sure. All right, so Lauren will take that, and then, yep, these two gentlemen.
I don't want to focus on the negative. I'm sorry. I don't want to focus on the negative, but I do want to call on your engineering expertise. What does deorbiting the ISS look like in terms of dismantling and getting it safely out of orbit? I'm sure a lot of thought's been put into that already.
Oh yeah, that's a good question for Mr. Gerstenmaier. I don't even want to think about the station coming down. Are you kidding me? I know there are teams that are working that. You know, there's a whole process by which that has to happen. It's all controlled and safe, right?
We had to file an environmental impact statement, and we have
We got a mic coming.
procedure to deorbit station. So we have a detailed procedure to deorbit station. It'll actually take, we believe, 2 or 3 progress vehicles to do it when it comes time, and we'll aim for a spot over the ocean, but we don't actually deconstruct it. It actually comes down in one piece, and we've spent a lot of time studying how we would do that when it comes time. But we don't talk much about that, and we don't think much about that. But just like NASA does always, we're prepared. You know, we hope for the best, and we're prepared for the worst. So when the time comes, we're ready to do what we need to do. But we've got really detailed plans. We can share those with you.
Thanks. We have one more question in the middle. Yep.
I just had a curiosity of a question. How close is NASA working with the private sector on doing research in space? I mean, are y'all developing stuff together?
Yeah, it's a really good question. The development of privatized research and investigations actually goes through the National Lab component, and that is managed by CASIS. It's a nonprofit organization, which is the way you manage national labs, by the way, on Earth. So CASIS is the Center for Advancement in Science and Space, and they are their goal and what they do every day is to work with private industry to build research portfolios that benefit the industry and those of us here on Earth through use of space station.
Probably have time for 2 more. Let's take the first one.
Hi, I'm Grace Draper, and I was wondering what powers the International Space Station?
Well, what powers the International Space Station? I always get the good questions from the students. Solar panels. A lot of things, but solar panels every now and then provide the power. Every now and then the station will get a boost as well, either from a visiting vehicle to keep it in its orbit. Let's see, is there anything else I should mention with regard to vehicle? I think that's probably pretty much it. It's more complicated than that, but.
Down your right.
Hi. What further research is in the works to advance growing on the station and for our plants? And what time frame do you think we're looking at for being able to cultivate those plants for a reliable food source?
Okay, good question. So plants. Again, Dr. Marshall Porterfield could share some of that with you too, because that's his expertise. But so we have a payload coming up, I think at the end of this year, slated for SpaceX 3, that's called the Veggie. We'll have a demonstration of it, I think, next. The Veggie payload is designed to have twofold purposes. One, we're interested in the scientific happenings of plants, what actually goes on in all parts of plant growth. So from a scientific perspective, we're interested. But from a food growth interest, the Veggie is supposed to also be like a precursor at designing hardware that could support food growth, plants that could be used to eat. So not just from a scientific perspective, but what does it really take? What kind of lighting, what kind of environmental control does it take to grow foods that can be consumed, grow plants that could be consumed? So look for Veggie at the end of this year. In the outcoming years, there's also an advanced plant habitat that's being designed and will be sent up as well to look at more effects of microgravity on plants. Plants are so terrestrial. I mean, for millions of years, billions of years, they've evolved in the gravity environment. And so so taking them out of their natural habitat is like removing us as well. So lots of stuff happens, and there are lots of communities looking at plants. And so, so the goal for the next few years is to put all that data together and try to come up with a complete story so that we can advance crop growth in space and also on Earth.
All right, please help me thank Dr. Tara Rilla. Here we go.
Thank you. Thank you.
A perfect segue, actually, as we wheel out this experiment. Our final guest today is Dr. Marshall Porterfield. He is the Division Director of NASA's Space Life and Physical Sciences Research and Applications Division. In this capacity, he oversees and manages fundamental space biology, physical sciences, and all human research within NASA while providing oversight to the International Space Station National Lab. The projects and long-duration experiments in microgravity managed by his division are designed to ensure the health of former, current, and future flight crews. They allow continuous and interactive research similar to Earth-based laboratories while enabling scientists to pursue innovations and discoveries not currently achievable by other means. And I saw this in his office the other day, and I said, please, I promise we won't break it. Can we get this down in the auditorium? And he said, no problem. So thank him, and please help me welcome Dr. Marshall Porterfield.
Thanks so much for this opportunity to get together with everyone and share what's going on in the Division, Life and Physical Sciences at NASA headquarters. We're currently gearing up really for a new era, a new dawn, circling above us about 220 miles at a speed of 17,000 miles an hour is the most advanced laboratory ever conceived or built by humans. Our division is focused on using the ISS space station to develop the science that will lead to the technology that will allow humans to explore further out into the solar system. So that's kind of the journey I want to take us on and describing what we're doing. I was asked originally to talk about the Human Research Program. So I am going to talk about the Human Research Program and some of the highlights in terms of developing countermeasures that are going to protect astronauts as we potentially move out to the asteroids and move out to on a mission to Mars or permanently man a moon base. But I'm so glad that people were so interested in plants and that we actually have this is a prototype of Veggie. It's going to be launched on SpaceX 2, and its purpose is to do science, but also to test ability of of NASA to develop a salad machine. And so the idea is that the astronauts can grow some greens to nibble on from time to time. I have it in my office for show and tell, but I also have an ulterior motive because I'm going to grow salad in there. And every once in a while, I'm going to grab a head out and I'm going to go throw it at Gerstenmaier and say, I need some more money for research, please. So next slide. So also, I was asked to tell everyone a little bit about myself. I just came to NASA about 6 months ago, started in August officially. I'm here by way of Purdue University. I'm actually on leave of absence from Purdue University. Bowler up. I'm professor of biological engineering. I've been involved with space-based research since my graduate school days. I was supported as a graduate student where I did my PhD at LSU. Go Tigers. By a NASA Graduate Student Researcher Fellowship. So I've been involved with space-based research since beginning of my PhD work. I've worked on 5 shuttle-based experiments, and we've flown a couple campaigns on the reduced gravity flight platform that NASA maintains. So does anybody know the nickname for this? Vomit Comet. So I guess I've tallied it up. I've spent 45 minutes of my life in microgravity. It was a great experience. And everybody I think here probably maybe knows how this plane operates, but basically it flies parabolas. So when the plane gets at the top of the hill, it's like when you're driving in a car kind of fast at the top of a hill or a roller coaster, you feel a little wee. So this is a big wee. For about 30 seconds, microgravity, and at the bottom of the hill, you hit 2 Gs. So if you're not used to this and you're standing up, the blood's going to move from your head when you hit 2 Gs and come back up and go back down. And what's in between your feet and your head? Your stomach. That's where
you don't eat first.
I've seen people make that mistake. I didn't. All the campaigns we've flown with students, none of the Purdue students have ever gotten sick. So we have, at least my teams, we have a perfect track record, but MIT wasn't as fortunate. So. Next slide. So earlier we learned that this is 50-year anniversary of John Glenn's initial flight. This is Ed White doing the first American spacewalk. These early space explorers only were probably in space long enough to experience some of the early symptoms of, so there's space acclimation symptoms. It's basically things like nausea, headache, vertigo, kind of like car sickness, but it's like space sickness. Later on, as astronauts started to do longer duration missions, like going to the moon and Skylab and Soyuz Apollo, we learned more about how the body adapts to the microgravity environment. So we're still mostly in low Earth orbit. We're not really dealing with the topic of radiation yet. So we're talking about the body's adaptation to the microgravity environment. Life has evolved over 4.1 billion years of the history of this planet under the constant force of gravity. That's the only thing that's really been constant in the evolution of biological systems in on the planet. So it's novel now to have the opportunity to look at humans and other biological model systems like plants. And the Life and Physical Sciences Research Division covers the Human Research Program, which is more applied in trying to develop countermeasures, but we also, the program includes fundamental space biology, where we're doing things like microbial observatory. We're working with other model organisms like nematodes and yeast and cell biology systems that are really important for us to be able to learn more about how life adapts to space. Humans, long duration in space, suffer from more serious conditions associated with decrease in cardiac output, vestibular responses that are altered, like Don talked about, his readaptation, bone and muscle wasting, decreased red blood cell counts, immune deficiencies in space. But out of all of those, the 2 most serious are probably bone and muscle wasting, which is why the astronauts exercise so much. And I'm going to review the capabilities on the ISS in order to support astronaut health and essentially try to solve that problem. So astronauts can, I think there are cases of astronauts losing 15 to 30% of their bone mass on some of the early International Space Station expeditions over 6 months. So if you think about what a long duration transit to Mars would entail, potentially you may have astronauts arriving at where they're going to explore but unable to walk. So it's really important to keep astronauts healthy, to protect their health so they return to Earth and they can recover and they can lead a quasi-normal life, Don? Approximately. Next slide. This is a picture of Sergei Krikalev. Sorry, I'm not really good at pronouncing Russian. He's doing some work, some exercises on the bicycle ergometer. This system is also interfaced with the Human Research Facility. There's a Human Research Facility 1 and Human Research Facility 2 that includes all kinds of biomedical equipment for monitoring crew health, but also for doing human research and doing biomedical research. There have been bicycle ergometers even back on the Skylab days. So this is a really important capability for maintaining crew health and also for documenting changes in terms of biomedical research. Next slide. This is Sunita Williams. This is one of the early resistive exercise systems that was developed and flown on International Space Station. It's called the IRAD, the Interim Resistive Exercise Device. Interim because they were always planning on building a better one, which I'll show you pictures of later on. You can see the kind of the straps and pulleys and the shoulder harness. This device allows you to do things like squats and curls and pull-ups and general resistive exercises like that. Next slide. And this is Dan Burbank. This is the ARAD. It's a more advanced piece of equipment. And what it does is it uses pistons and vacuum tubes in conjunction with flywheels to provide more inertial feedback. So as the astronauts are actually doing exercise, it has more of the real feel of moving weights in a 1G environment. And a really important study was published this year by some of the Human Research Program investigators from a university that were funded by NASA, and they found that a combination of using some bisphosphate drugs and the ARAD device allowed them to really do a good job of protecting the astronauts from bone health, to the point where we're fairly confident that we might be very close to solving that, closing the gap on that risk to astronaut health. And as Don mentioned before, the astronauts, it's a lot of hard work to get that protection, because they get to work out 2 hours a day over a long period of time. So they usually come back healthier than when they went up. Next slide. Here's Sunita Williams on the early version of the treadmill. The new version, the Colbert, is operational now. And you didn't fail to mention that the urine recycler, they gave John Stewart the option of having that named after him. I think it was the space toilet, environmental water recycling thingy, or I think that's what it. He declined though, so. So this is Sunita's a big fan. I'm a big fan of hers, I have to say, because she's the first person to run a triathlon in space. As you can imagine, she synced it up. She officially registered for the triathlon, started at the start of the race, but they had to figure out something extra for the swimming. So she actually did ARAD exercises to simulate the swimming. She did the running on the treadmill, and she did the ergometer. Did I think an Olympics length triathlon. So this is a picture of the treadmill vibration isolation unit. And now the Colbert is equipped with, this unit required power because it has gyroscopes and active vibration dampening, and the Colbert, it's more passive, so it saves power in the station. Next slide. And again, there's a tremendous amount of biomedical research that goes on in terms of monitoring cardiovascular output. There are many other biomedical problems that astronauts face in low Earth orbit we still need to continue to do research in. And as we continue to move out into the solar system and potentially explore the Moon and Mars, we are going to have to deal with the radiation problem. We already are doing a lot of research in that area in terms of collaboration with Brookhaven National Labs and DOE. NASA and DOE do a lot of work together. We're working with biomedical model systems. Obviously, we're now exposing humans to radiation. So that's really the next main risk that we're going to have to deal with. An alternative way to deal with the risk is have people out there at shorter times. Right? So if you have faster rockets, you have a shorter transit time, the radiation exposure is less. Some of the data coming back from the Mars rover recently that was published suggested that you do get a minimal amount of shielding from the atmosphere, the weak atmosphere of Mars, so that changes some of the calculations of timelines and transits for conducting human research. So one last slide. Another big highlight, actually I have two more slides. Another big highlight is the announcement of the one-year mission. Scott Kelly and Mikhail Konyenko are going to be doing basically double duty on the space station, one-year missions. And this again is to try to learn more about how the human body adapts to microgravity. We're going to do more standardized biomedical research. As a lot of you are aware, the Russians have done a lot of long duration human missions on Mir, and they've learned a lot from those opportunities. But we have a lot more tools now available to us to do more detailed biomedical research. So that is really one of the key objectives in terms of the ISS, in terms of utilization, is try to figure out how we get more out of it scientifically. Because we do have a grand challenge to potentially go to Mars. So next slide. So I'm going to close out my talk about Human Research Program and maybe answer some questions about plants. I like to show these artist renderings, especially when I'm talking to students, because I really like the imagination, the vision of the artist, and trying to project a future for human exploration. As many of you are aware, you know the quote of Albert Einstein, who said, imagination is more important than knowledge. But in this case, we're going to need both. We're going to need imagination and knowledge in order to fulfill these kinds of goals. So thank you very much for your attention. Thank you very much for your time, and I'll be happy to answer questions.
Yep, let's go.
What's the difference between using a pink light to grow the plants and a normal light?
Okay, so what you see in here, there's actually two types of LEDs. So NASA actually started doing the first, I remember when I was a graduate student, and the first blue LED panels came from Japan, and NASA scientists grew plants with blue LEDs. They were the first ones to do it. So there's actually blue and red in there. So the reason we're only using blue and red is because the plants only use blue and red light to do photosynthesis. They reflect the green wavelengths of light, so that's why plants look green to our eyes. So if we were to build a lighting system on the space station or on a spacecraft to grow plants to provide food, we wouldn't want to use power to power white lights for the plants to grow, because we would just be basically wasting electrons making green photons that were just going to bounce off the leaf anyway, right? So it's more efficient to do it this way. So this system is set up. You can change the ratio of the red lights to blue lights. And so basically chlorophyll in the plants absorbs those two wavelengths only. So it's basically we can couple the light production directly into the photosynthetic apparatus in the plant. It's much more efficient. Now, a really cool thing about this is it's not only is it more efficient for space flight, it's actually more efficient on the ground. So what the technologies, the hydroponic, aeroponic technologies, and these lighting systems have now sprung up a new industry urban and vertical farming. So there's an example in Chicago, a meat packing plant has been converted into an urban farm. They provide high quality produce to restaurants, and they're able to use indoor growing systems with LEDs because they can save money. It's cheaper to do that than to buy it, than to grow it out in the countryside in a field where you have to use herbicides and pesticides and then ship it into town. So this is actually a brand new industry that's springing up all around that is attracting a lot of venture capital and a lot of startup funding right now to start these kinds of operations.
Okay, do you have one to your left? Go ahead. Or if we haven't ready to go ahead, on the right.
Okay. One of my hobbies is home brewing, and I think I heard you mention yeasts earlier, and I was just wondering, in general, how do yeasts do in space?
So one of the things in general that you see with biological systems in space is that they don't tend to do as well in space as they do on the ground. And part of the explanation for that is biophysical. So Don was talking about how bubbles and separate from fluids. You have to have some kind of centrifugal force in order to give you some kind of, basically a convection in microgravity. It turns out there is, in microgravity, one of the major factors that impacts microorganisms and organisms like plants is the fact that fluids and gases don't behave. There's no convection. They become diffusion limited. So in a culture system, you have to be very careful about how you design it. You can always have little corners here where you don't have complete mixing. Obviously, plants don't have any way. They're pretty passive in terms, they're waiting for gases to move over the leaves, but if the gases don't move over the leaves, they'll become limited either in photosynthesis or in oxygen uptake. So that's really one of the main things that we have to consider about the microgravity environment is it's a fundamental, but it's not only the gravity sensing aspect of it, it's the biophysics. Now, humans don't have problems with the diffusion limitation because we have mechanical ventilation system, right? We have lungs. But other organisms are much more challenged because of that aspect in microgravity.
Okay, to your left.
So it's thrilling how many more things there are to study. It also sounds a little bit daunting. How do you prioritize the research you conduct? And is it mapped back towards a goal like sustained human life in space or the next outing in space? What do you measure it against, and how do you choose what's on deck?
We want to do two things. We want to advance fundamental knowledge for the sake of advancing fundamental knowledge, but also have that be targeted towards the mission of human exploration. Right now, it's been about 2 years now since a decadal survey came out from the National Academy of Sciences, and in that document was somewhat prioritized in terms of what types of science we should be pursuing within the Life and Physical Sciences Research Division. It is challenging because of logistics of doing work in space, hardware development. Throughput is really a key limitation right now. So we're actually, I think, right now on the verge of reinventing the way you do life and physical sciences research, because we're creating an open source innovation approach to doing research. So instead of having a hypothesis and a PI the way we've done it in the past, we're going to use more advanced technologies like all the omics technologies, genomics, proteomics, and do massive experiments for communities, and then use bioinformatics to allow people to mine those databases and do systems biology on spaceflight responses. We think we can increase our throughput, and we can get, these are going to be open source. So that means everyone can have access to it, undergraduate students, and also kids, I think, will be doing their science fair projects based on ISS research within a couple of years.
All right, unfortunately, that's going to have to be the last question. That's all the time we have for today, but the conversation doesn't have to stop here. You can find all the ways to connect with NASA on social media at www.nasa.gov/connect. In fact, in just 2 days, there's a great opportunity to join in another real-time conversation about the International Space Station. And a first for the agency, we'll host a live Google Plus Hangout with the International Space Station this Friday, February 22nd, from 10:30 to 11:30 a.m. During the event, astronauts aboard the station and on the ground will be answering several video questions that were submitted on YouTube, but you'll have your opportunity to submit real-time questions as well on Google+, Twitter, and Facebook. You can find out more about that event at nasa.gov/social. Finally, to get the latest news on the astronauts and the work they're doing aboard the space station, including how they're getting ready to receive new science experiments next week on next week's SpaceX launch out of the Kennedy Space Center, check out nasa.gov/station. Please help me thank all of our guest speakers today. Thank you.